Welcome back. We've been talking about multiple regression, modeling a response variable as a function of two or more explanatory or predictor variables. Now, thus far in this discussion, we've looked at how to estimate the parameters in that kind of a model, the beta parameters, which would include the intercept and the slope coefficients, as well as the variance of the error term in that model. Now, in this next lecture, what we're going to look at is how to test hypotheses about the parameters in that model, in particular about the beta parameters. We're going to look at how to test the overall significance of the model, but we're also going to look and see how to test custom hypotheses about one or more of those slope coefficients. So let's get into it. In this lecture video, we look at hypothesis testing involving the multiple linear regression model. Now, up to this point, we've looked at estimation in the context of the multiple regression model. Once we've estimated those parameters, we have some additional questions to answer. The first would be, what is the overall adequacy of the model? And the second would be, which specific explanatory variables are important? Now, I think I might like to rephrase these two questions a little bit. For the first question, I would say that what is the significance of the overall model? Now, I like that term significance better than adequacy because you can have a significant model that is not adequate, right? So I would rephrase that first question. What is the significance of the overall model? And then the second question would be, which of the explanatory variables seem to be significant in predicting or explaining the variability in the response? So let's take a look at how to answer these kinds of questions. In this section, we look at four cases. We test for the significance of the regression, sometimes called the global test of model adequacy or model significance. We look at tests on individual regression coefficients, and that would also include groups of coefficients. We'll look at the special case of hypothesis testing when there are orthogonal columns in the design matrix X, and then we'll look at testing the general linear hypothesis. Now, the first question, again, is what is the significance of the overall model? And that's what we're looking at right now. So the test for the significance of the overall model is a test to determine whether there is a linear relationship between the response variable and any of those explanatory variables. The null hypothesis that's being tested is that all of the slope coefficients are zero. In other words, that the response variable is not linearly related to any of the response variables. The alternative hypothesis would be the opposite of that, which would be that at least one of those slope coefficients is non-zero. Another way to say that would be that the response variable is linearly related to at least one of those slope coefficients. And so that's the test, or these are the hypotheses that are being tested by that overall test. Now, as you'll recall from chapter 2, the total sum of squares in the response can be partitioned into two pieces or two parts. The sum of squares due to the regression model, and then the sum of squares residual, or that which is not accounted for by the model. And you'll also recall that we use that partitioning to compute mean squares associated with the regression and mean squares associated with the error term or the residual. And we use that in performing an ANOVA test or an ANOVA type test, an F test, to test the significance of that model. Well, we can do the same type of thing in the context of multiple linear regression. And so the way to do this is to calculate the sum of squares due to the regression, the sum of squares due that are total in the response, and then we can get the sum of squares residual by subtraction. But there are also ways to get them directly, as you're seeing in these formulas. And so to get the total sum of squares, we could calculate it this way. We start off in this formulation. We have the uncorrected sum of squares of the responses. And then from that, we subtract what's called a correction factor or correction term. Basically, it's correcting for the mean. And so what this gives us then overall is the corrected sum of squares of the observed y values. All right. And then to get the sum of squares for the regression, here is one formula that we can use. And this is basically the first term is an inner product of the prediction vector, the y hat, with the observed y values. And then from that, we subtract off, as we did here, the correction for the mean. The formula for the sum of squares error, or the sum of squares residual, as they're denoting it in these notes and in the textbook, is obtained using this formula. So it's the difference between the uncorrected sum of squares of the response vector and then this inner product of the predicted y vector and with the observed y vector. Now, this is just an algebraic simplification of the inner product of the error vector, or the residual vector itself. All right, so you can calculate it a couple different ways, but this is the way that they're showing it in the textbook. Now, once we've calculated those values, we can organize that work in the form of an ANOVA table. And so we've got basically we've got our source of variation column, all right, and we've got the total variation in the response, and we're partitioning that into two pieces, the variability that is accounted for by the regression and the variability in the response that is not accounted for by the regression, and that's what we call the residual. In some output, you'll see it called error, all right? And then we have the sum of squares column, and again, we have the total sum of squares, SST, as they're denoting it here. This is the total corrected sum of squares in the response. We partition that into two pieces, the sum of squares due to the regression or accounted for by the regression, and then the sum of squares that's residual, that is not accounted for by the model. Associated with each of these degrees of freedom would be the number of degrees of freedom. Associated with the sum of squares, we have degrees of freedom. And so there are k degrees of freedom associated with the regression sum of squares. There are n-1 total degrees of freedom. And then the difference between the two, n-1 minus k, all right, would be the degrees of freedom associated with the sum of squares residual. And then, as you'll recall, we divide the sum of squares regression and the sum of squares residual, or the sum of squares error, by their corresponding degrees of freedom. And that gives us the values for the mean square column. So the mean square for the regression and the mean squared error, or as they're denoting it here, the mean squared residual. And then once we have these two mean squares, which, by the way, are stochastically independent, then we take their ratio, and because they're independent, that ratio has an F distribution. And if the null hypothesis is true, again, the null hypothesis being that those beta coefficients, and more specifically, the slope coefficients are all 0. If that is in fact true, then this F statistic has an F distribution with k numerator degrees of freedom and n minus k minus 1 denominator degrees of freedom. And so the rejection criterion would be to reject the null hypothesis and conclude that the alternative hypothesis is true if the calculated value of the F statistic is greater than the upper alpha percentage point of the F distribution with k numerator degrees of freedom and n minus k minus 1 denominator degrees of freedom. Now, what they're showing on this slide, and this is a screenshot from the textbook that they're using, they're showing that the expected value of the mean squared error is always sigma squared. It's always the variance of that error term in the multiple regression model. The expected value of the mean square for the regression is equal to sigma squared plus this quadratic form. And in general, this quadratic form value would be positive, and so the expected value of the mean squared for the regression would be something larger than sigma squared. But if that null hypothesis is true, if all of those slope coefficients are zero, then this term, this quadratic form term, would be zero. And so in that case, the mean squared for the regression and the mean squared error would have the same expected value. They would both be equal to sigma squared. And so the ratio of the mean squared regression to the mean squared error would tend to be close to 1 in those, and that when the null hypothesis is true, because they would both be unbiased estimators of sigma squared. But if the null hypothesis is not true, then this quadratic form term would be positive, and therefore the mean squared regression would tend to be larger than the mean squared error. And so that is why we're looking for large values of the test statistic f-calc to lead us to rejection, because the large values of f correspond to the alternative hypothesis being true. So that is what they're talking about here on this slide. They're also giving us a little bit of information about the non-centrality parameter of the f statistic in the case that the alternative hypothesis is true. Okay, so they're looking at the delivery time data set in example 3.3, and they're showing the calculations. And so they're starting off by calculating the total sum of squares, the total corrected sum of squares of the response. And they do this using this formula here. And so they start off by calculating the uncorrected sum of squares of the y values, which is 18,310.629. And then from that, they're subtracting off this correction for the mean. All right, so you can see here that you add up the values in that y vector, or in other words, add up the response values, square that sum, and then divide by n, which in this case is 25. So the sum of all the responses for all 25 observations is 559.6. We square that, divide it by n, which is 25. Subtract that from the uncorrected sum of squares of the y values. And so to get this, obviously, what you would do, or one way to do it would be to square each of the y values and then add those squared values up. All right. And then you do the subtraction and you get 5,784.5246. So that is the total sum of squares, the total corrected sum of squares for the response. Now, next, what they're doing is calculating the sum of squares due to the regression. All right, and they're using this formula here that we've already discussed. All right, the inner product of the prediction vector with the observed vector, and then subtracting off this correction factor, which we've already used up here. And so when they do that, they get 5,550.8166. So we've got 2 out of the 3 sums of squares. We know that because this is a partitioning, we know that the sum of squares regression and the sum of squares error add up to the total sum of squares. And so since we have the total sum of squares and the sum of squares regression, we could get the sum of squares error by subtracting the 5,550.8166 from the 5,784.5426. All right, and that's indeed what they do. All right. You could also get it directly by using this formula. And, you know, that's sometimes a good thing to do. It's sometimes a good idea to calculate, for example, the sum of squares error directly using this formula, and then also calculate it via the difference between the total sum of squares and the sum of squares regression, and just make sure that you're getting the same value, because if you're not, there's an error in the calculation somewhere. But if you're using software, if you're programming your own or something, and you want to verify that the programming is correct, that's a situation where you may want to do this, do both methods of calculation. All right, but once you've validated the software, you would only need to do it one way. Okay, so then in this particular example, remember we've got two explanatory variables. X1 is the number of cases, and X2 is the distance walked by the delivery person. And so the overall test of the model, or the test of the overall model, the null hypothesis would be that the slope coefficients on both X1 and X2 are 0. In other words, the null hypothesis is that the delivery time is not linearly related to either the number of cases nor the distance walked. All right, and so in order to test that hypothesis, we go ahead and calculate the mean squared due to the regression, the mean squared error, and take that ratio. All right, now the numerator, the mean squared regression, they've calculated as 2,775.4083. All right, and the mean squared the mean squared error essentially is 10.6239. And when you take that ratio, you get 261.24, which is a very large F value. All right, and so there's a very, very strong evidence that the null hypothesis, again, this null hypothesis right here, there's very strong evidence in the data that that null hypothesis is not true. Now, where did they get the values for the mean squared regression and the mean squared error? Well, again, what they've done is they've calculated the sums of squares, the total corrected sum of squares, the regression sum of squares, and the residual sum of squares. And then they've divided each of the mean squared, the sum of squares regression and the sum of squares residual or error by their corresponding degrees of freedom. And so the 2775 was obtained by dividing the sum of squares due to the regression by 2. Likewise, the 10.6239 is obtained by dividing the sum of squares error or sum of squares residual by 22, and so you get 10.6239. And then finally, the F statistic, F calc I like to call it, the calculated value of the test statistic is the ratio of those two mean squares, the 2,775.4083 divided by 10.6239, and that gives a calculated F statistic value of 261.24. And remember, we're looking for large values of that F statistic to lead us to reject that null hypothesis that neither of those two slope coefficients are 0. And that is in fact quite large for an F value. In fact, the P value is very, very, very close to 0, 4.7 times 10 to the negative 16. So you can see that this is a very, very significant test. There's strong evidence that at least one of those two slope coefficients is non-zero. Okay, in addition to performing tests of the overall significance of the model, it's often good to get a feel for what proportion of the total variability in the response is accounted for by your regression model. And that value, that proportion, is provided by what is called the coefficient of determination, which is denoted R squared. All right, and it's denoted R squared because in the case of simple linear regression, it's the square of the correlation coefficient between your response and your single explanatory variable. So again, the R squared value, the coefficient of determination, is equal to, or what it gives you is the proportion of the total variability in the response that is accounted for by your regression model. And if we go back in this example and look at the ANOVA table for the regression, for this particular situation, for this model with this data, the R squared is going to be equal to the sum of squares regression divided by the total sum of squares. Because by definition, the R squared value, the coefficient of determination, is the proportion of that total variability that is accounted for by the regression. So it's the ratio of the sum of squares regression to the total sum of squares. Now, the point that they're making here in this second line here is that the R squared value increases anytime you add more explanatory variables to your model, even if those explanatory variables are really not contributing. All right, even if they're not linearly related to the response, just by virtue of adding a variable, you can increase the value of R squared. Perhaps not much, but it will increase. And so, we need to keep that in mind and take R squared values with a grain of salt. Now, perhaps a better version or a better measure to use would be what's called the adjusted R squared. And the adjusted R squared is based on the actual R squared, but it penalizes the R squared for the number of terms in the model. All right, and in particular, if a term that's added into a model is not significant, then your adjusted R squared will more than likely decrease. So the adjusted R squared is accounting for the number of terms in the model and whether those terms are significant. And so it gets around this problem, or alleviates this problem of the R squared value increasing just by virtue of adding an explanatory variable or two. And so here they're giving a numerical example. So suppose that the total sum of squares is 245. There are 15 observations. And suppose that the sum of squares error with 3 explanatory variables is 90. Then using the formula for the adjusted R squared, your adjusted R squared would be 0.53. Now compare that value of the adjusted R squared of 0.53 with what the actual R squared would be. The actual R squared would be 245 minus 90 all over 245, which would be about 0.63. All right, and you can see here that there's quite a reduction in going from R squared to the adjusted R squared, and it would be it's because perhaps some of those variables are not significant. Right, now suppose that a fourth regressor is added and that the sum of squares residual is 88. And so in that case, the adjusted R squared actually decreases. All right, and so you can see that it's gone from 0.53 to 0.49, even though we've added an additional explanatory variable. And so that may indicate to us as well that that fourth explanatory variable is not carrying, it's not carrying its weight, it's not pulling its load. Okay, next we look at how to test hypotheses about individual regression coefficients. So instead of the global hypothesis, where we're testing the hypothesis that all of those slope coefficients are 0, once we've performed that test, and if we conclude that, well, if we reject that the null hypothesis of that overall test, and therefore conclude that at least one of those, one of the explanatory variables in the model is significant, or in other words, at least one of the slope coefficients is non-zero, then the natural follow-up question would be, okay, which slope coefficients are 0? And so then that leads to additional tests. Perhaps we look at tests involving each of the individual explanatory variables by themselves and their slope coefficients. And so, for example, if we were going to do that, then we could look at the null hypothesis that a particular slope coefficient is 0. against the alternative that it's not 0. And the test statistic for this, that we could either do it as a t-test or as an f-test, right? And what we're looking at here is how to do it as a t-test. If you're using computer software, then in many cases, the tests for the individual slope coefficients or the individual explanatory variables would be represented or shown as t-tests, but you can also do them as an f-test. But let's look at this particular t-test. And so we have the basic form of a t-test, the numerator being the difference between the estimator of the quantity, the estimator of the parameter that we're testing hypotheses about, the difference between that and the hypothesized value. Well, in this case, the hypothesized value of beta j is 0. So we have beta hat j minus 0. So it's just written as beta hat j. And then we divide that by the standard error, the estimated standard error of the point estimator. So the estimated standard error of beta hat j. Now remember that the standard error of an estimator is the standard deviation of the sampling distribution of that estimator. Okay, and you'll recall from your reading in the notes and previous lecture that the covariance matrix of the of the beta coefficients is given by the inverse of x prime x. Now, in the book, that x prime x matrix, I'm sorry, the inverse of the x prime x matrix is denoted by bold C. And then the individual entries in that matrix are denoted by C sub ij. Now, the jth diagonal entry in that C matrix, or equivalently, the jth diagonal entry of the inverse of x prime x is the estimated standard deviation of beta hat j. And so it gives, I'm sorry, it's, we have to multiply that by sigma hat squared. And once you do that, then and take the square root, then you get the estimated standard error of beta hat j. So again, the jth diagonal entry of the inverse of x prime x, when multiplied by the MSE from the model, which is the estimate of the error variance, that gives us the estimated variance of beta hat j, and we take the square root of that to get that standard deviation. Okay, so that's how we calculate the t-statistic for this particular test. And then the rejection criterion is to reject the null hypothesis if the test statistic, t-calc, is either less than the negative of the upper alpha over 2 percentage point of the t distribution with n minus k minus 1 degrees of freedom, or greater than the positive value. All right, and so the easiest way or an economical way to state both of those criteria is to say that we're going to reject if the absolute value of t-calc is greater than the upper alpha over 2 percentage point of the t distribution with n minus k minus 1 degrees of freedom. Now, the way that they're showing this right here, they're showing a two-tailed test, which is what we've got here. You could also, if it made sense in the context of a particular problem, to perform a one-tailed test, and then you would, if it was a right-tailed test, if you're trying to show that beta j is greater than 0 as opposed to being less than 0, greater than or equal to 0, I'm sorry, greater than 0 as opposed to less than or equal to 0, then you would reject for large values. And again, in that situation, you would not divide the alpha by 2. And if you wanted to perform a left-tailed test, then you would reject for small values of t-calc. And again, it would be, and you would not have the absolute value in that case. You would reject if t-calc is less than negative t sub alpha, comma n minus k minus 1. So anyway, they're only showing the two-tailed test here, but I think you're familiar enough with these hypothesis testing type of situations that you could very easily know how to do those one-tailed tests if you needed that without having it explicitly written here. Now, the other thing that they're saying here is that, and it's good to keep this in mind, that this is what is called a partial test. And what that means is that what we're going to be, the way that we're going to be doing this test is that we would be testing the null hypothesis that beta j is equal to 0, given that all of the other explanatory variables are in the model. All right, and so that is why it's called a partial test. Now, how do we go about conducting the test? Well, we're going to use the what's called the extra sum of squares method or principle to come up with the appropriate way of testing hypotheses on individual parameters, but also, and perhaps more interestingly, on groups or collections or subsets of the beta coefficients. And so let's start off by, again, looking at the matrix representation of the multiple regression model, where we've got k explanatory variables or regressors. And so in this case, the y vector is n by 1. So we've got n rows in one column, so we've got n observations. The X matrix, the design matrix, has dimensions n by p, so again, n observations, and we've got the number of columns in that X matrix is p. Beta, the parameter vector, is p by 1, and then epsilon is the n by 1 error term. And also, p, the number of parameters here, is k plus 1, k being the number of slopes, and then we have one additional parameter, beta 0, the intercept. All right, so we want to determine if some subset of the regressors contributes significantly to the regression model. In other words, we want to perform a hypothesis test for a subset of those slope coefficients. Let's let the number of slope coefficients that we want to test a hypothesis about together be denoted by R. And so then what we're going to do is we're going to take that parameter vector, the beta vector, and we're going to partition it into two pieces. Now, the second piece down here, beta 2, what we're denoting by beta, bold beta 2, that is the set of slope coefficients that we're wanting to test hypotheses about. And so the dimension of that subvector is R by 1, right, as indicated here. And given that, and because beta itself has dimension p by 1, then that would mean that beta 1 has, it's a p minus r by 1. So it's got the p minus r slope coefficients that we're not testing hypotheses about. And then what we're wanting to do here is test the null hypothesis that the slopes contained in beta 2 are all equal to 0. And that's represented by this vector quality here, the vector beta 2 being equal to the 0 vector of the same dimension. Now, with that decomposition and with a corresponding decomposition of the X matrix or design matrix, we can rewrite the matrix formula for the model, y equal to x beta plus epsilon, as y equal to x1 beta 1 plus x2 beta 2 plus epsilon. Now, because both of those vectors, x1 beta 1 and x2 beta 2, because they're both in the model, this is still the full model, but it's a decompositioning of that x times beta. Now, for the full model, as you know, we covered this in a previous lecture, we know how to estimate beta. Now, I just want to point out here that there's a beta, there should be a beta, there should be a hat on that beta, but it when they took the screenshot, that hat got cut out. And so we know that beta hat, which is our least squares estimator of beta, is given by the product of the inverse of x prime x and x prime y. the regression sum of squares associated with this full model is given by beta hat. And once we have beta hat, so beta hat prime times x prime times y. All right, and so that is the sum of squares for the regression for the full model. And there are p degrees of freedom associated with that model. All right, and then the mean squares error associated with the full model, again, as you'll recall, is given by this expression here. All right, and so we have the sum of squares error divided by its associated degrees of freedom. So we have y prime y, right, that uncorrected sum of squares of the response minus, and then beta hat prime times x prime times y. All right, so that gives us the mean squared error associated with the full model. Now, to evaluate the significance of the explanatory variables whose slope coefficients are contained in this beta 2 vector, in other words, to evaluate and assess the contribution of those explanatory variables, we fit a separate regression model. We fit a separate model that imposes the condition of the null hypothesis. In other words, we fit a model that imposes the restriction that the slope coefficients on the slope coefficients in the beta 2 vector are all 0. All right, and so we call that the reduced model. Now, let me go back up one slide. If the beta 2 vector is 0, in other words, if that null hypothesis is true, then the product of x2 times beta 2 is going to be 0. And so then the model simplifies to this reduced model. Now, what we need to do next is to estimate beta 1 given this reduced model. Well, we know how to do that because this is just another multiple regression model. And so we can apply what we already know to estimating beta 1 in this reduced model. And in fact, it would just be the product, well, number one, it's denoted by beta 1 hat, and it's equal to the product of the inverse of x prime 1 or x1 prime times x1 times x1 prime times y. So x1 prime times x1, quantity inverse, times x1 prime y. Okay, I think I said that correctly. All right, so once we have that, in the same way that we got the sum of squares up here, once we had beta hat, we can get the sum of squares for the regression for the reduced model using the analogous or the same formula, basically, just replacing beta hat and x with beta 1 hat and x1. So the sum of squares for the regression for the reduced model would be beta 1 hat times x1 prime times y. Now, for this model, there we have p minus r degrees of freedom. Okay, so once we have those two sums of squares, the sums of squares for the regressions for the full model, all right, denoted by that quantity there in equation 3.34, and the sum of squares for the reduced model, all right, then we take the difference and we denote that difference using this notation. So this is the sum of squares for the regression for beta 2, given that beta 1 is in the model, essentially, all right? And so this is, in words, we describe this as the regression sum of squares due to beta 2, given that beta 1 is already in the model. And so we said that the test we were performing here is a conditional or a partial test. And this is why, or that's reflected in how we're describing it and in this notation. Now, associated with this regression sum of squares due to beta 2, given that beta 1 is in the model, that sum of squares, that regression sum of squares, has associated with it r degrees of freedom. And that this sum of squares is called the extra sum of squares due to beta 2 because it measures the increase in the regression sum of squares that results from adding the explanatory variables that are associated with the coefficients in that beta 2 vector. Now, this quantity, this extra sum of squares, is independent of the sum of squares, and in particular independent of the mean squares for the full model. And so what that means is that if we divide that extra sum of squares by its degrees of freedom, which is R, and then divide that quantity by the mean squares error for the full model, then we again have an F statistic that we can use to formally test the hypothesis that beta 2 is equal to 0. All right. And so this is how we form the test statistic. Again, we calculate that extra sum of squares due to beta 2, given that beta 1's in the model. Once we have that, we divide it by its associated degrees of freedom, which is R. And again, what is R? R is the number, it's the dimension, it's the number of rows in beta 2, but the other way to think about it, it's the number of slope coefficients that we're testing are all equal to 0. Okay, so once we have that test statistic, we need to know whether or not to reject the null hypothesis. And that rejection criterion is to reject the null hypothesis if this test statistic exceeds the upper alpha percentage point of the F distribution with R numerator degrees of freedom and N minus P denominator degrees of freedom. And so if that's the case, if F calc here exceeds that upper alpha percentage point, then we would reject this null hypothesis. We would conclude that that beta 2 vector is not equal to the 0 vector. And so that implies that at least one of those slope coefficients contained in that beta 2 vector are non-zero. In other words, we would be concluding that at least that the response variable is linearly related to at least one of those corresponding explanatory variables, given that the other variables are in the model that are associated with the beta 1 vector. Now, again, because this is it's a partial test, and so some folks call this a partial F test, again because we're looking at the contribution of the explanatory variables in X2, taking into account that the other variables contained in X1 are already in the model. All right, next we look at, and just discuss the situation where columns in the X matrix are orthogonal. And so if that's the case, if the columns X1 are in fact, if all the columns in X1, remember we've got this partitioning of the X matrix. So if the columns in the X1 component are orthogonal to the columns in X2, then that sum of squares due to beta 2 is going to be free of any dependence on the regressors in X1. In other words, it's going to be independent of those other variables that are already in the model. And so let's look at this example. So consider you've got a data set with 4 regressor variables, 4 explanatory variables, and then a single response variable Y. We fit the multiple regression equation with all 4 regressors, and we get the following fitted model. So Y hat equal to, and then this expression here. All right, so suppose that in looking at the t-test for the individual explanatory variables, we conclude that X3 is not significant. All right, and so we choose to, at that point, we may choose to delete it from the model. So what would be the equation if we did that? Right, if we remove X3 from the model, what would be the parameter estimates for beta 0, beta 1, beta 2, and beta 4? Well, in general, if we remove X3, then and if we were to refit that model, then the new coefficients would not be equal to the coefficients that we have obtained from this model. And the reason is because in that case, x3 is not orthogonal to x1, x2, nor x4. All right, so if we were to remove x3, we would need to refit the model completely, right, to come up with new parameter estimates. And in doing that, let's suppose that we get this fitted model here. So you can see that those coefficients are different. And so when the columns in the X matrix are not orthogonal, and in particular, when we're looking at testing hypotheses about a subset of those explanatory variables, if they're not orthogonal to the others, then you certainly need to, you absolutely have to refit the model if you're going to drop one or more of those variables. However, if the columns are orthogonal, then there's no need to refit because those parameter estimates are independent of the other variables in the model. And so the question here is, can you think of some situations in the real world, in real life, where we would have orthogonal columns? Can you think of some situations in the data that you collect, that you generate when you do your experiments, that would have orthogonal columns? Okay, so that's all we're going to talk about, at least in this lecture video on hypothesis testing. We are going to look at some examples, but I'm going to do that in another video. This one's getting a little bit long, and so what I'll do is I'll stop the video here, and then we'll continue on with the next topic, which is confidence interval estimation in multiple linear regression. But I'm also going to create one or more additional lecture videos that look at the examples that they talked about in these notes, example 3.3 and such. And we'll do that using some software.